Boom! Greetings, I'm KGKK and I've learned a few bits of cool stuff here and there, mostly from the interweb, some from friends, some from teachers, some from parents. And yes, there are a lot of sources which explain it a lot better than me, but I would not be your personal in house overconfident narcissist if I did not explain it better. Since I desperately need viewer attention, let's start out with the coolest thing black holes. And boom, peekaboo. The whiteboard is now a chalkboard. Deal with it. I like it that way, and you're gonna like it that way too because I can draw dotted lines on it, and I'm very proud of it. Now, first of all, many thanks to Spintown, my IRL friend, for teaching me this, and I'm very happy I learned it because this is very cool. And what I got out of it is even cooler. Of course, we're talking about black holes, so let's start off with something basic. The force of gravity. Specifically, this formula. Very common, very easy to understand, derived in hundreds of books, and I am not bothering to do so. Now, there's a thing called gravitational potential energy. You may have seen it being represented by you in many places, and its formula being given as mgh, where h is the height. Yes, this is right but wrong because this mostly works on Earth. If we're looking at any object in the universe, and every object is affected by gravity within the universe, the formula goes a bit more complicated per se. Let's start off with what is energy. Energy is just the ability to do work, and work is force into displacement into cos theta. And for our purposes, we have been doing it with D. So let's stick with D. And as you can see, it's pretty simple. But here's the thing. Gravity, for most of these calculations, will be acting opposite to how the object is moving. I.e., if there is, say, a rocket on Earth, and it's trying to leave, gravity will slow it down. Get my point? If there is, say, a photon trying to escape a black hole, its gravity will slow it down. So, the course we will be taking of 180 degrees, which is just -1. So, this will be our LHS, left hand side of our equation, as doing with the orange pen because it's an important equation. Force equal force into displacement into -1 equals, get this is interesting, the original formula we had for gravity, just put it in. We get G m over d squared. Make sense? Now get this. Make sense? Just the d's cancelling out. Now, -1 over here, we get as a final the universal, no, not the universal gravitational potential energy, which is represented by U, to equal -G m over d. Very important, even note it down in the corner. Now, moving on to something derived from this formula, or something actually a bit similar to it. We know that energy, the total energy of any system, at least for most of what we're looking at, is just kinetic energy kinetic, plus gravitational potential energy. Make sense? Of course it does. It's the simplest thing ever. actually mechanical energy of anything. Now, what we see from this, energy kinetic is just 1 by half mv squared. And yeah, this is negative. I was mistaken the corner notation. I am stupid. It was negative. As you see, this is very simple, and this, because it's negative, is just a negative, and because it's a negative, we can rewrite it as this beautiful thing. Now, because it's on the other side, now it won't be negative. G m in over d squared. D squared. I keep getting confused. Man, these are complicated equations, but I'm gonna tell you this. This video has been taken in many takes, and what you're saying is right. You can be assured. Now, the m cancels out on both sides. The 2 goes here, that becomes v squared equals 2g m over d. This may be starting to look similar because if we take the under root of both sides, v equals under root 2g m over d. And what's v? The escape velocity. So basically just the speed you need to be going to escape the gravitational field of the object. It's already getting cool, right? Another important thing, let's note it down in the corner. Pretty cool equation if I say so myself. You may be wondering, what the hell has this got to do with black holes? The transition is surprisingly simple because just replacing the v with light speed, commonly represented as c in scientific terminology, a great example of c being light speed is E equals mc squared, which is just energy equal to mass into the square of light speed. So yeah, c equals under root 2g m over d. Now, because we're in black holes, as of course the C says, because the escape velocity is just a bit greater than light speed, so not even light can escape, this just becomes r, the radius of the black hole. And this is actually what we're going to find out, the Schwarzschild radius, the length at which everything just goes into the black hole, the event horizon per se, the Schwarzschild radius. So we can rewrite this taking the under root of, we get, I should probably rewritten this, but I guess this also works, c squared equal to 2gm over r. And now cross multiplying, we just get r. Radius Schwarzschild equals 2gm over c squared. And that's it. To find the Schwarzschild radius of any black hole, we just don't have to know its mass, because all these other things, constants. Pretty cool if I say so myself. To the corner it goes. The corner is getting pretty crowded, but no need to worry because we are on our final equation before I tell you the coolest thing you will ever hear. Schwarzschild radius. What was it? Rs equals 2gm over c squared. Make sense? Of course it does. Now, if we take m over here, which is just m, makes sense, we can rearrange this entire equation obviously to be something like this. The mass of a black hole, or the critical mass of anything before it becomes a black hole, first child radius into c squared over 2 the gravitational constant. And you know what? If we just do a bit of bippity boppity, because I'm too lazy to do it in front of you, because this video is probably way too long already, and there are 3 more cool facts which you'll probably love even more than this one, even though this one was way too lengthy. We can do these calculations which are added in post. Wait, probably for a bit longer. And get that the amount of steel required to form a black hole is much. That's it. That's the critical mass for steel. This much steel and you'd have a black hole. In other words, this much. Boom, there you go. 10 raised to the power 38 kilograms of steel and you have a black hole. Share this to your friends to flex. And if they ask why, you can share them this video. Please, it's good for retention. Boom. On to fact number 2. You thought it was over? No, it's not. We're just getting started. This could be the coolest application of units I know. And to begin with that, we need to talk about cars. No, not that one. I'm not talking about Lightning McQueen. More like these. Too expensive. More like these. Yeah, I guess that makes more sense. This. Can remove them? Thanks, yeah. Those were the Alto 800, King Alto, and the Hyundai i10. Some cool things about these. Number 1, they're old, reliable, everybody loves them. Find me a single person who can hate on these, and I can tell you they've already been hated upon by others. Second of all, when you look at their backs, you'll see something. The i10 or sometimes the i20, though they're very rare to find, has written 1.2 behind them. And the Alto 800, as in its name, has 800. What are these referring to? Most of you may know this. Liter and cc, or cubic centimeters is just milliliters. I don't know why they do that. cc, just please tell me. That sounds like Sheldon's nephew. But yeah, some do cc, some do ml. I prefer ml because it's scientific. This is actually the internal volume of the pistons of any car, and it just tells you how much torque a car has. It's pretty easy to calculate. Just fill up the cylinders with water or just figure it out in CAD before you even made the car. But that's not what we're here for. How do you calculate the torque, or how do you compare the torque of electric vehicles? Because they don't have petrol, you can't compare the volume of fuel inside their engines, can you? Here's what you do. I'm now going to do a very bad drawing of an electric motor. Told you, this is an electric motor. Sometimes only one, sometimes two, sometimes three, and rarely four. No, rarely three, and sometimes four motors are in an electric car. And the best way to compare torque is just look at the torque of the motors. You may be saying, KGKK, I was about to say my real name. I ain't gonna dox myself, alright? You might be saying, KGKK, how do we calculate the torque of motors? torque is just angular force. Fair enough? Yeah, because that's just how much force you can do at an angle. Alright, let's forget the angular aspect of it and just look at force. F equals ma is the simplest formula ever. Make sense? How would we calculate torque? It would just be how much weight can a motor get up to a speed of 1 meter per second within 1 meter. Basically, how many newtons of force can it apply? And how do we calculate that again? This is the SG90 microservo, probably the most common servo when it comes to electronics and microcomputing out there, because this cheap, I wouldn't say durable because this breaks all the time. In fact, this is a broken one, has written on it, this probably flipped for you guys, microservo 9 grams. Now what's 9 grams? The mass it can get to from rest to 1 meter per second within 1 meter. That means this little bad boy has 0.009 or 9 thousandths newtons of torque. Get this now. This little thing, how was it calculated again? I've actually done this experiment before and I'm too lazy to show it. So I'll draw it instead. Imagine you have friends, because of course you don't. And there's one friend who can change the load in a basket which was originally weightless or a known weight. Alright? And there's this guy, he's changing the weights and he's telling you. And you are a guy who is operating a lever which turns on and off an electric motor. Now this electric motor is winding the string, and you're seeing how fast it can wind the string for different weights. Each motor does it differently, so you take a batch of about 10 motors usually and you test it for about 3 different weights. So basically a sample size of 30, and then it's just pretty easy to calculate. So yeah, the answer was a pulley. So yeah, also the torque of brakes is also measured in newtons for obvious reasons. So in electric cars, everything is in newtons. Like, share, subscribe.